Hey everybody, today we're going to be getting into section 11.7 and we're going to be comparing areas and volumes of similar solids. Okay, we've been doing a lot of work with surface area, volume, that sort of thing for three-dimensional figures for solids. Okay, now we're going to be looking at the relationships between their surface areas and volumes if those solids are in fact similar. Alright? So we're going to be actually going back to section 10.4 to remember what happened when we had scale factors and what happened with the areas if we made things blow up by a certain scale factor. All right, and that's going to serve as a reminder of what we're going to be doing or setting the table for what we're going to be doing in this section. Okay, so the first half dozen slides are actually going to be talking about stuff that we did back in section 10.4. And so let's go right into it. See if we remember this. These slides are actually duplicated from that other video, but remember what we did back then. We said, look, we're just going to take some random figure, okay? And I happened to make it a rectangle because it was simple, and we made one rectangle that had sides of 5 and 12. And then I said, what happens if we double every dimension, okay? Or blow it up by a scale factor of 1 to 2, right? We can make that scale factor look like this, huh? All right, well, let's see what happens to the perimeter and what happens to the area. Well, the perimeter, after we calculated it out, we found out that the perimeter was changed also by the scale factor of 1 to 2. Okay, now they're written differently, but you see that the perimeter and the scale factor match identically depending on how you write it. All right, but then we also said, hey, let's look at this. What happens to the area? And we did the calculations on that, and we found out that the area changed by a factor of 4 to 1. And we said, you know, that makes sense actually, because now if I duplicated this, you know, I could actually fit 4 of those guys in the area that is occupied by the bigger one. All right? So, we found out that the area changed in that manner. All right. Then we took one and we blew it up by a scale factor of 3. All right? So if we make every size triple in going from one figure to the next, well, we check the perimeter. Hey, perimeter of the big one was also triple the size of the small one. But then when we checked the area, we found out that it was 9 times as big. And again, makes sense. We could look at this figure and actually fit 9 of those little rectangles. 1, 2, 3, 4, 5, 6, 7, 8, 9 on the area, the bigger one. Okay, so it led us to this finding, that if the scale factor of two similar figures is A over B, then the ratio of their perimeters is also A over B. But the ratio of their areas changes by A squared over B squared. And we worked on problems like this. All right, this again still duplicated from that section 10.4, so you don't necessarily have to take it down. You've already got it in your notes. But we have a problem here where I got two similar octagons. Okay, remember, similar figures are ones that have basically the same shape, although they may have different sizes. And what is involved there is that all angles are going to be the same, and all sides have to be proportional. So the proportion on these sides leads us to our scale factor, right? The 4 and the 10 tell us that the scale factor has to be something related to 4 to 10. We can simplify that to 2 over 5 if we want. But then, as we talk about the areas, we squared both of those numbers to say, you know what, the ratio of the areas has to change by the factor of 4 over 25. And that's the ratio that we use when we set up our proportion to solve a problem like this. The area of the little guy was 77.12. The area of the big guy would have to change by a factor related to that area ratio of 4 over 25. That's what we use to cross multiply and divide to find out the area of the bigger figure. All right, so I hope you remember that. Let's go to the other kind of problem that we did. Okay, so in this case, I'm giving you the areas and asking you what is the ratio of their perimeters. Well, we take the area ratio. I could simplify it down to that, and then when I take the square root of the two numbers, basically I know that this ratio has to be A squared over B squared, or the plain old scale factor has to take the square roots, and thus the perimeter also has to take the square roots. So, remembering that, What happens now when we get into volume? All right, plain and simple, guys. Check out what happens with the area. Well, if I take this one top side, look, got 1, 2, 3, 4. If I double the size, okay? In other words, explain. Get into this, Minardi. All right. If I take this one figure and actually change it by doubling every dimension, well, you'll see that the area, once again, will change by a factor of 4. Every one of these sides, see the top, how I can fit 4 of the original tops onto the bigger top, 4 of the original front sides, 4 of the original front sides onto the new front side. So if I double every dimension, the area still changes by a factor of 4. But check out the volume. I can fit not just 4 of these little red boxes into the new figure. I can actually fit 1, 2, 3, 4, 5, 6, 7, 8 of those boxes into the new figure. That means if we double every dimension, the surface area increases by 4 times, but the volume increased by 8 times. Look at another one. Here's our original figure. What happens if we triple every side? So instead of making each side twice as big, now what happens if we make every side 3 times as big? Same thing is going to happen, say on the top. Instead of one top surface, I now have 9. Same with the front. See the 9 of them here. And the side. Okay, so every surface area changes by a factor of 9, which makes sense from what we did before. If we have a scale factor of 1 to 3, the areas change by 1 to 9. But look what happens to the volume. I got a boatload of boxes here. I got 9 in this front layer. I got 9 boxes in this middle layer. I got 9 boxes in this back layer. We increased the volume by 27 times. Okay, now you're going to see the pattern that comes out of this. All right, so if the scale factor is 1 to 3, the area factor is 1 to 9, the volume is 1 to 27. We compare that to what we had here. We see that the pattern is going to emerge all the time. That if our scale factor is A over B, well, our surface area is still going to change by A squared over B squared, just like it did before, but the ratio of the volumes, we are going to cube those numbers, right? Going back to where we were, we take 3 cubed to get 27. Here we took 3 squared to get the area, okay? Same back here. What we had here for every surface area was 2 squared when we doubled it, 2 cubed when we tripled it, or when we look at the volume, okay? All right, so that's important, folks. A squared, A over B for the scale factor. A squared over B squared gives us the surface areas, and A cubed over B cubed gives us the volumes. So let's show you how this works. All right. First of all, are these two solids similar? Well, our definition of similar solids is going to involve the fact that, well, all the angles have to be the same, all the surfaces have to be the same general shape, and all the sides have to be proportional. Well, sure enough, I got a proportion that says 5 to 6. Well, 10 to 12 reduces to the same fraction. Okay, 5 to 6 is equal to 10 over 12. And if that happens, we know that we're going to have similar solids because the ratio of all the dimensions is the same. All right, so now, if they are similar solids, they are, what's the ratio of their surface areas and their volumes? Well, I kind of went the long way about it. I can show you the old-fashioned method. Okay, we can calculate the surface area and the volume, right? So for the smaller solid, I'm going to use our formula for the surface area of a cylinder. Okay, 2 pi r squared plus 2 pi rh. Plug in 5 for the radius, 10 for the height. Okay, solve that out, and I get 150 pi. For the larger one, I'm going to use 6 for the radius, 12 for the height, do the same thing, and I'm going to get 216 pi. So our ratio then is 150 pi over 216 pi. which can simplify down by canceling the pi's and then dividing out by 6, and we get 25 over 36. For volume, we can do the same thing using our volume formula for a cylinder, pi r squared h, figure it out for the smaller solid, figure it out for the larger solid, make our fraction, simplify, and we find out that that's 125 over 216. Okay, we could do it that way, but we don't have to now because we have a new trick. Our second trick is that let's just use those ratios like we spelled out on that last page. Okay, the yellow over here, right? If the scale factor is 5 to 6, the surface area has to change by a factor of 25 to 36, same numbers we had before. And the volume would have to change by a factor of 125 to 216 because that's 5 cubed over 6 cubed. Okay? Now, when it comes to solving problems like this, here's an example that I want to walk through with you. Scale factor of two similar prisms have surface areas. Find the scale factor if the surface areas are 288 and 648. Okay, these next few examples I'm going to show you, and I'm going to probably go fairly quick, but what I want to do is show you how I deal with these. I think about them in terms of 3 columns. I got a yellow column, a green column, and a blue column, okay? Doesn't matter yellow, green, blue, but anyway, what I do with them is I look at making a scale factor column where I'm going to list A over B. Surface area, I'm going to list A squared over B squared. And volume, I remember that's going to be A cubed over B cubed. Okay, so I'm going to look at those 3 columns. First thing I want to do, I'm going to take what I'm given. And that was that the surface area has a ratio 288 to 648. Okay, if it's helpful, we can simplify that. And by dividing by 2, I find out that I get those numbers. And you know what? That is helpful. Because remember, now this is A squared over B squared. These numbers both happen to be perfect squares. So when I take the square root of them, we get 12 over 18. Nice and easy. You can reduce that and find out that my surface area scale factor, the surface area of this means that the scale factor originally had to be 2 over 3. Similar problem on this next slide, okay? But now instead of just asking you for the scale factor, I'm going to ask you what's the ratio of the volumes. But I'm going to do the same thing. I'm going to take what I'm given, put that in the surface area factor because what is given, surface area column, because what's given to me is surface areas of 108 and 192. So I'm putting that in the second column. And I'm going to reduce if it's helpful. When I divide by 3, I get this. I can take the square root. And the reason I do the columns, guys, is because 99% of the time, we're going to need to go back to this scale factor column so that we can then work our way into the other 2 columns. All right? So I'll show you how, again, that's going to work. Here we're given the scale factor, but they're asking us to find the volume factor. Our problem is we've got to go this way first. Okay? So once I know that my surface area factor simplifies to that, I can take the square root of those and find out that my scale factor is 6 to 8. When I see that, I can simplify. Now take that 3 over 4, and since the volume factor is A over B cubed, I'll cube them both, and I know my surface area, or my volume factor, has to be 27 to 64. Okay? Okay. Next example. Okay, ratio of surface areas of 2 similar pyramids with these volumes. You'll see again, now I'm given volumes, so I start in the third column. Okay, now those do simplify actually. If I take the cube root of all of those, and again, here's how we do it on the calculator. Okay, we can hit this math button, go down to the cube root command, number 4 there, and if I take the cube root of 729 and hit enter, it tells me that it's 9. Okay, I could do the same thing with the 1331, find out that it's 11. So I know that when I take my A cubed over B cubed, I simplify it to a scale factor of 9 over 11. That won't reduce or simplify any, But those are the numbers I can use when I square them now to find the surface area factor of 81 over 121. Okay, 9 squared over 11 squared. Okay, a couple more examples. Now, this time I'm going to ask you something new. Not just going to ask you for what's the scale factor. I'm actually going to ask you to do some math on it. Okay, and you can pause and try this on your own if you want. But we have 2 paint cans with lateral areas. So area factors is where I'm going to start. The question is going to ask this one though. What is the volume of the larger can if the volume of the smaller one is 1157? So again, I'm going to start with my 3 columns, start with what I'm given. Now, I can't reduce those, so when I take the square root, I'm just going to use the decimal numbers here. Okay? Those are the numbers that I'll cube to find my volume factor. Since the question is asking for what's a volume, this is what I need to use, the cubed values from A over B. Okay, so using that ratio, that 32,000 over 80, whatever, that's where I'm going to set up my X over the unknown, right? I'm sorry, my unknown volume of the larger can over the volume of the smaller can. Since they're giving me a volume and asking me for the volume of the larger can, I'm going to set it up this way, making sure that I use the volume ratio from the 3rd column right there. Okay, then I cross multiply divide. I can find the value of the volume of the larger can. Okay? Okay. Look that over, make sure it makes sense to you. One more example. Marble paperweight weighs 0.15 pounds. If we got a similarly shaped figure, marble paperweight, and it's 3 times as large, what's that new figure going to weigh? Well, start with our columns. What I'm given is a 1 over 3. Volume is a function, or weight is a function of volume, so I'm going to cube both of those numbers, get 1 over 27, and use that 1 over 27 ratio to compare the weight of my smaller figure to the weight of the larger one. When I cross multiply, we'll find 4.05 pounds. So go back over it again, guys, if you need, and I will see you later.